Welcome everyone to another lesson on Khadija Academy. Before we start this lesson, hit the subscribe button, the notification bell, and the like button for the YouTube algorithm. Now let's go and start our lesson. Hey guys, and welcome to another lesson. In today's lesson, we will discuss an important topic, which is the starting of our DC machines. So what I mean by starting of DC machines? Well, you will find that when we start our DC machine, at the very beginning, the electrical machines take very large amount of current, which can exceed even the rated current. Now, why is this happening? Now, remember that we have E, or the back EMF, equal to phi Zn P over A, right, 60A. At the very beginning of our electrical machine, DC motor, we have our supply, right? V terminal, okay? That gives us a current. One current goes to the armature and one goes to the shunt to provide excitation. At the very beginning of DC motors, the speed of this motor is equal to 0, right? So it means that at the very beginning, when N equal to 0, the back EMF equal to 0. So what is the problem of this? You will find that at the very beginning that the equation of current is equal to V minus E back, right, from KVL here, okay, from KVL here, divided by R armature. So when E back, or at the very beginning, E back equal to 0, it will be I armature will be V terminal over R armature. Now this value can reach 6 to 8 times the value of the rated current, which is a very large amount of current. So this is actually a problem in starting of DC machines. So at starting of the motor is stationary, so the speed is equal to 0, E back equal to 0, V over RA is very large. This high starting current has some issues. Number one, it can cause the burning of the armature due to excessive heating. Number two, why excessive heating? Because the heating is as a result of IA square multiplied by R armature. The power losses is very high at the very beginning. Damage of commutator and the brushes because they cannot withstand this amount of large current. In addition to excessive voltage drop, you can see that voltage drop here, IA multiplied by the resistance. Since IA is very large, then voltage drop on the armature is very large. So in order to avoid this starting effect, we add a variable resistance in series with our armature. This variable resistance is known as the starting resistance. Okay, so this resistance is variable. We add it at the very beginning of our electrical machine. So when we add an additional resistance or starting, our current, this resistance will increase, leading to current going down. Okay. Now, as you will see that this resistance is variable, it is not a constant resistance. We change it as it is reduced as the motor gains speed, and it cuts out completely after the motor gains its own full speed. Okay. So what you can see that this is a configuration that you will find in many electrical machines. So we have our terminal voltage, we have our field winding here, RF, and the inductance of the field. This is our field winding, and we have our induced EMF or the armature circuit. Now in series with the armature circuit, we will have our variable resistance, the starting resistance. Okay, so what you can see that at the beginning when the motor is off, this is open circuit. Okay, we don't have any kind of supply. Okay, now when the motor starts, as you can see here, when the connected DC was to be started, the lever, this lever here, is turned gradually to the right. So it starts at the first position of 1, like this. So we will have all of this resistance R1, all of this added in series, which makes So it will be plus RA1 or R1, whatever it is. Okay, so the current will be limited. Instead of having 6 times or 8 times or whatever, it will be reduced to the specific value that I need. Let's say, for example, maximum 2 times the rated current. Okay, so when lever touches point 1, the field 1 is connected to, as you can see here, connected to the supply, and the armature winding gets connected with resistance R1 to R5. So we have 1, 2, 3, 4, 5 resistance in series. Now during starting, at which we will have the 0 back EMF, the full resistance added in series with the armature winding. Okay, so what you will find that as the speed of the motor starts going up, so as the speed of motor, so when N, instead of being 0, it will start going up. So what does this mean? E back also will start going up. Okay, so E back will start going up. So what I'm going to do, if I keep everything, if I keep this resistance, the current will start going down more. So what I'm going to do is that I will start removing resistance. So instead of having this large resistance, I will have a smaller one, this only. Okay, by removing this and connecting to number 2. Okay, so we will have smaller resistance making current going up again, and etc. As the speed reaches the rated speed, we cut this resistance completely from the armature circuit. And in this case, we are going to be connected at the position, this position, which is the run position, using an electromagnet. Okay, so what you can see that here, this position will be our final position. So you can see that the current from the supply will go like this, part of it will go to the field, and the other part will go like this through the armature. So we will not have any kind of resistance at the run position. And this electromagnet keeps holding the position at run until we disconnect our supply. So this will return back to the off position automatically when there is no supply voltage. Now let's have an example number 3 in order to understand how are we going to do the starting method. So number 1, we have a DC machine of a 10 kilowatt 1000 RPM and an armature resistance of 0.1 connected to a 100 volt DC supply. So our supply here 100 volt and the resistance of the armature 0.1. Determine the starting current if no starting resistance is applied and the rated current of the machine. Find the value of REE to limit the current to double its rated value, the starting current to limit the current to double its rated value, and find the value of resistance steps and number of steps to limit the current between 100% to 100% of the rated value. So this is basically the design of starting of the machine. Okay, so let's start step by step. Number 1, we need starting current. Okay, so we know that from KVL that I armature equal to V terminal minus E back over R armature. Now at starting, E back is equal to 0. So our I armature at starting will be V terminal over RA. V terminal 100 volt DC supply, R armature 0.1. Okay, so this is the first solution. I start without any starting resistance equal to 1000 amperes. Okay, what about the rated current of the machine? Okay, how can I get it? Very easy. As you can see that we have 10 kilowatt. So we have power equal to 10 kilowatt and we have our voltage equal to 100 volt. Okay, so we can say that the starting current will be or the rated current of the machine is 10 divided by 100 volt, right? So 10 kilowatt divided by 100 gives us 100 amperes. Okay, great. So what we can see here right now is that the starting current compared to rated current, starting current is 10 times I rated, right? So very large amount of current that can damage our windings or our machine, commutators, brushes, everything. So what I'm going to do is that I need a resistance to be added to limit the current to double its value. So double its value, it means that the current will be 2 multiplied by I rated, which means 200 ampere. That is the current I need, maximum current at starting. Okay, so our current equal to V terminal over R armature plus the additional resistance RE1. Okay, so our current 200 amperes, V terminal 100 volt, okay, and RA plus RAE, okay. Okay, so our armature 0.1 and we can get REE. So as you can see here, equal to 200 amperes, V terminal over the new resistance plus the armature resistance. This gives us the starting resistance to be 0.4. So what is this resistance exactly? All of this. RAE1 equal to 0.4 ohms in series with the armature resistance of 0.1 ohms. Okay, now what I'm going to do, or the next requirement, is that I need to know the value of resistance steps and the number of steps to limit current between 100 to 200. So I need to know how many steps we have and the resistance of each step. Okay, so how can I do this? Okay, let's understand what I need exactly. So here, as you can see, that we need to limit our current between 100 ampere, which is the rated, to double rated value. So at the starting, since we added REE at starting, at the very beginning, all of our resistance here, our current at the very beginning when E back equal to 0, okay, at this beginning, the current will be 200 amperes, right? And we know that as the speed goes up, okay, of this motor, E back will go up, right? So as E back go up, I armature will start going down, right? Here we still have the resistance, okay, we still have RE1, okay, and as speed increase, the E back increase, I armature will start going down. So as you can see, it will start going down until reaching the 100 amperes. If I don't do anything, or remove the resistance, any part of the resistance, then the current will start going down like this. Okay, because E back increases at the same resistance, I armature will keep going down. So I don't need this. I want it to fluctuate between 100 to 200. Between 100 and 200. So at this point, I will prevent it from going down. How can I prevent it from going down? By removing some resistance to make it go up to 200 amperes once more. Okay, so at this point when it drops down to 100 amperes, I will remove part of the resistance, make the new resistance RE2, remove this one and make new resistance RE2. So when the resistance goes down, the current will start going up once more to the 200 amperes point. And then after E back increases once more, current will start dropping again, right? And then when it reaches 100 amperes, I will remove another resistance, this one. So we will have RE3 and etc. So let's see what are we going to do exactly, okay? So number one, I have here RE1 equal 0.4, the whole resistance. I would like to know when the current drops down to 100 amperes, when IA equal to 100 amperes, what is the E back generated? So we have RA plus RE1. This is 0.4, this is 100 volt, this one is 0.1, and I would like to know the new E back when the current drops down to 100 amperes. The E back that makes it goes all the way down to 100 amperes. So like this. So E back will be I armature R armature, V minus I armature R armature, V minus I armature R armature. So we have 100 volt, our supply, minus 100 amperes at this point, minus the total resistance, which is 0.1 plus 0.4. So it means that in order for our current to go from 200 to 100, we need 50 volt generated as a E back. Okay, very nice. Now I would like to, at this specific point when we have E back equal 50, I would like to make the current go up again to 200 amperes. So in order for the current, so the current will be V minus E back divided by the resistance. So I will get the new resistance right now. So our E, our current will go from 100 to 200 by removing a resistance. So I would like to know at this point what is the new R. What is RE2? This resistance. So I would like the resistance, and I know that the current will be 200 amperes at the same E back 50 volt with the same supply 100 volt. So what about the new resistance? So again here, it will be 100 minus 50 divided by 200 gives us the new resistance. So in order for the current to go up again, we need the resistance to drop down from 0.4, okay, not 0.4 only, okay. Remember that the total resistance for this equation, this R total originally is RE1 plus R armature, okay. This is our total resistance, okay, which was originally 0.4 plus 0.1 gives us 0.5, okay. Now here the new resistance will be 0.25, okay. The new resistance will be 0.25. So what is our resistance right now, or what is our drop right now? So our resistance was originally 0.5. It will be now 0.25, okay, which is REE2, which is this resistance. The new resistance 0.25 is RE2 plus the armature resistance, right? This is the resistance, total resistance that will make it 200 amperes once more. So in order to get RE2 only, I will subtract from this value the armature value. So it will be 0.25 minus 0.1, which is the armature resistance, gives us 0.15 ohms. So again, if you don't understand it, let's repeat this. So we have originally a resistance of 0.4, which is the total starting resistance, plus 0.1, which is the armature resistance, okay, which is 0.5. Now, in order to make the current goes from 100 amperes to 200 amperes, the resistance will go to half its value, which is 0.25, right? So the new resistance here of this armature at this position, for example, it will be this resistance plus armature resistance. So I would like to know this step only. This step only, this part only, is 0.15 ohms after subtracting our armature. Now what again? I'm going to wait for the current to go down due to increase in E back. So I would like to know new E back, so the 100 amperes at this point, when the resistance will be R armature plus RE2, right, at the new resistance, which is all of this is 0.25 and terminal 100 volt. Now get the new E back. So E back will be V terminal minus IA RA2, which is the 0.15 plus 0.1, which is a 0.25. This will give us a new back EMF 75. Now I will remove another resistance. To get RE3, I will remove a resistance. So we are going to step number 3 to raise the current once more to 200 ampere. Okay, so to raise it again to 200 ampere, it will be V minus E back over 200 amperes, right? V minus E back over 200 amperes, which will be 0.125. Now remember, this resistance here, the new resistance is the variable resistance RE3 plus R armature. So in order to get only RE3, I will remove 0.1, which is the resistance of the armature. Gives us this step of 0.025 ohms. Okay, so we have RE1, RE2, and RE3, right? Okay. Now what? Now I would like to know the next step. To get the next step, simply we have at this point current goes down to 100 amperes. So at 100 amperes, I would like to know E back at the new resistance which is 0.125. Okay, and the back 100 like this. So the new E back will be 100 minus I armature 100 multiplied by 0.125 gives us 87.5. Similarly, I would like to know what will happen next. I would like to know at a 200 ampere, what will be our resistance? So RA to increase the current to 200 amperes will be V terminal, which is 100 minus the new E back divided by the current 200 amperes. So it gives us the new resistance 0.062. So for the current to go from here to here, we should have a resistance of 0.0625. This resistance is R armature plus RE4, right? However, as you can see, R armature itself alone is 0.1, which means it is not possible, okay? Which means this one is the last point for us. How can I know this? If you subtract 0.1, which is the resistance of the armature, then what will be RE4? RE4 will be a negative value, which is rejected, right? We can't add a negative resistance. So in this case, we will have only like this. We have resistance between 1 and 2, resistance between 2 and 3, right? And then we will have the run position. So how many steps you have? We have 1, 2, and 3, right? Resistance RE1, RE2, and RE3. Okay, RE3 like this. So what is the resistance that we have, or the value of the resistance? Or the value of these resistance R1, R2, R3. R1 will be this resistance. This resistance will be RE1 minus RE2. R2 will be RE2 minus RE3. R3, RE3 minus RE4. Like this. Now, of course, we don't have except R1 and R2 because we don't have R3. Why? Because R3 is IE3 minus RE4, and RE4 is a negative value, so we don't have this step here. So we only have two resistance, R1 and R2. So it will be like this. So as if we have, so let me draw it for you, these steps. So we have 1, 2, and we have 1, 2, 3, and the run position, run, right? Like here, 1, 2, 3, 4, 5, and between it and the run, there is a resistance. Okay, so this is our starting. So the first, so R1, first resistance will be 0.25. Second resistance will be 0.125 ohms. Okay, and the last one is this one, RE3, which is 0.025. Now, as you can see at the very beginning, we take all of this RE1, which will be, if you sum all of this, it will be 0.4 ohms. In the second position, like this, we will have all of this resistance, which will be 0.25, right? 0.15, right? RE2, 0.15, all of this. Then in the last position, or step 3, we will have 0.025, and then after this we will go to the run position. Okay, so this is how you design the starting of a DC machine. Thank you for watching this lesson. I would like to invite you to our academy, Khadija Academy Premium membership, which will help you learn more about electrical engineering. In this academy, or in the academy membership, you will find that we'll have more than 100 courses in math, electrical engineering basics, power engineering career preparations. For example, we have electrical design, we have courses on electric circuits, power electronics, ETAB, MATLAB, solar energy, wave energy, wind energy, and much more. You will find also in this academy, you will find the different feedbacks from some of our students that joined our courses. You can, for example, join our membership for just a small fee per month, or you can just have a lifetime access in which you will get all of current courses and classes, and you can have them forever. And not only this, but any new courses that will be created, you will be able to watch it for completely free. So what are the classes that I will learn in this membership? You will find different classes in electric circuits, you will find in transformers, magnetic circuits, machines, power electronics, load estimation, lighting design, lightning also design, earthing system, cables, generators, light current systems or low current systems, off-grid design, on-grid design. Very lots of classes and courses in different topics. Okay, and you will find that inside, when you join this membership, you will find this blueprint that will guide you in which classes you will start with when you join this membership. So thank you, and see you in our membership on Khadija Academy.